When presenting your estimation results, we know that just providing the estimated parameters is not enough. For sure, we also need to know something about the precision of the estimates. But are we done yet? Here's our famous farmer again, who had a bridge built based on the estimated canal width and taking into account the precision as indicated here with the error bar. Clearly, he's still not happy with the result. Even though the precision is okay, apparently the accuracy is not. So we should ask ourselves, can we trust our solution? Can we be sure it is not contaminated by errors? In this module, we will look into this. Specifically, our goal is to detect errors which are not random errors. Remember that the influence of random errors is described by the precision of our estimation results, given by the covariance matrix of x hat. We can see from the equation that the precision only depends on the design matrix A and the covariance matrix QIY, which captures the uncertainty due to the random errors. Note, the precision does not depend on the actual observations. But how about the other two types of observations errors that may affect Y? The blunders and systematic biases. These kind of errors will obviously not be captured by the precision, but will influence the estimated parameters, as we have seen in the example of the farmer's bridge. Another type of error that we did not consider so far is a model error. For instance, a wrong choice of design matrix A or covariance matrix QIY. An incorrect model will impact the estimated parameters as well as the precision. But we cannot see it by just looking at the covariance matrix itself, since we don't know the correct one. So, if interested in the quality, just adding the precision when presenting the estimation results is not enough. We need to do something more. We need to test for the aforementioned types of errors in our data or model. Let's look at some examples based on a linear trend model for the height of a point. Here we see the unbiased observations and the estimated trend line in green. The error bars, more specifically the 95% confidence intervals, are shown as well. The first example will be where one of the observations is an outlier. On the right-hand side, we see the same observations, except that now the third observation contains a large error of 10 millimeters in this case. It is an outlier. We can immediately see the impact. The estimated trend line is different. Here the residuals are shown as well. We can see that not only the residual of the third observation is larger than in the unbiased case, but also the residuals of the second and the fourth observation are much larger. They are affected since the fitted line is pulled towards the erroneous observation. We'll come back to this. How about systematic biases? Here's an example where the last two observations are affected by a constant systematic bias. See the figure on the right and compare with the unbiased case. Again, the estimated trend line is different, and here again the residuals are shown. Interesting to see is that in this particular case, especially the residual of the second observation is much larger, whereas this observation does not contain a bias. Then a special case where all measurements are affected by the same constant systematic bias. The estimated trend line is completely shifted upwards, but the residuals are unchanged. Can we detect that something is wrong here if we only have this result? The final example is not about measurement errors, but a model error. What if we made the wrong assumption with regard to the functional model? In the figure on the right, we assumed a constant height, but actually the height is increasing linearly in time, as shown in the figure on the left. Again, the residuals are largely affected due to the wrong model choice. Based on the four examples, you may have a clue where to look at when you want to test for errors. We should evaluate the residuals. Large residuals indicate that the model and data do not seem to be consistent, and thus that something is wrong. But when is a residual too large? And if we find that residuals are too large, how come? What is the underlying error? In the next video, we will address the first question. The second question is for later.